Cue ball, 8 ball, cue ball, 8 ball, cue ball. Cue ball it is. Believe it or not, but everybody watching this video has both the skills and the equipment to measure the diameter of our sun directly from the comfort of your very own driveway, even though we are 93 million miles away. All you need is a mirror, some type of billiard ball, a piece of PVC, a tape measure, and some third grade math. In fact, the math is so straightforward that you can even do it with a gigantic slide rule. No, that's the wrong way. That's more like it, but don't worry, I'm not going to go full nerd on you. We will use a calculator just to speed things up a little bit. Stick with me until the end and you'll know exactly how big the sun really is, and you'll be able to say you proved it. It all comes down to two simple triangles, but the method is best explained with a good old-fashioned pinhole camera. Now, we're not going to use a pinhole camera for this video, but it does explain the process. Sunlight leaves the sun in all different directions, but we are only concerned about the light waves that travel all the way through space towards Earth. Now, of course, this is not drawn to scale. That distance from the sun is called an astronomical unit, or AU for short. If we're standing down here on the Earth with our pinhole camera, well, some of those sunlight rays come all the way here and they go through this hole in this membrane, and then they focus into a nice little round picture of the sun on the back of the box. And believe it or not, that layout that I just described sets up the two triangles that we need. They're drawn at vastly different scales. This side represents the diameter of the sun, and this represents the distance to the Earth. And of course, this side represents the inside of our pinhole camera box, or the technique that I'm about to show you. And this is the projected image of the sun. But let's take a look at what we've got. This is the full diameter of the sun, and when it comes to this triangle, we only get half of that, which is the radius. So we're going to call this radius sun. And this distance is the distance to Earth. So this is 1 astronomical unit. So this is roughly 150 million kilometers. But what do we have over here? Well, this distance is just from the front of the pinhole camera, or the front of the projection system we will be using, to the wall where the sun is. And so we'll just call this wall distance, right? And over here, we have the diameter of the projected sun, but we're only going to be interested in calculating half of that. We'll double it later. And we'll call that the radius of the projected sun image on the wall. Now, if you remember from school, you have similar triangles. The ratio of these two legs will be equal to the ratio of these two legs. So what does that mean? Well, let's make a fraction. We've got the radius of the sun divided by 150 million kilometers. We set that equal to
the radius of the image on the wall
divided by the wall distance. So we can measure this from the wall. We can measure this using a tape measure. So the only unknown is the radius of the sun, and we're going to solve for that. And it's really easy. You just multiply both sides of the equation by 150 million kilometers, and voila, here we go. The radius of the sun is equal to this fraction here. We've got the radius of the projected sun disk on the wall, and we have a distance from the wall to the mirror, and we multiply that by 150 million kilometers. So the sun rays are coming here, and they hit the very front of the pinhole camera, and there's a tiny little hole, and they keep on going, and they project an image of the sun onto the back of the box. So remember this view, because we're about to change it all up. We're actually going to put a mirror right here. Now, I know what you're saying. Replacing the hole with the mirror makes no sense, but it actually does. Those same light rays that came from the sun, well, they still coalesce right here at this tiny little hole, but instead of going straight through, they're going to reflect off that mirror. Like this. And they are going to go into a garage on your house. They're going to go into this dark room, and they're going to project onto a wall that you have, either in your garage or a shed, something like that. The advantage is that the mirror can be larger, it can bounce more light, and most importantly, it is extremely aimable. So you can aim it anywhere so that it goes on any part of the wall in the garage. Unlike a pinhole camera, which is really not aimable. Now, we're not going to use a pinhole camera for this video. The projected image is too faint and too small to get the kind of accuracy that I want for this project. But really, it's because I have a method that is way more fun, and it has the side benefit of really showing off sunspots. But it will require a billiard ball. My camera's overheating, so I'll go kind of quick. The method starts with a billiard ball. It doesn't need to be a cue ball, but this is one of the cheapest ones that you can get. You can buy them on Amazon. If you don't have one, I'll put a link to it down in the description box. Next, you need a piece of mirror that is coated on the front. Most household mirrors are coated on the back. Unfortunately, that means that when the sunlight is coming, it has to travel through about like a quarter of an inch of glass, bounce, and then travel back through, and you get refraction and all kinds of weird stuff. If you want a really sharp image, it needs to be coated on the front. Now, they do make small, tiny little mirrors that already have self-adhesive on the back. They're very thin, so the refraction might not actually be that bad. That's a great way to start this experiment if you want to give that a try. With this one, I just put a piece of double stick tape on the back, and I stick it to the billiard ball. Look at that. Now, you set this in a piece of PVC. This lets you point it and it stays put. Now, where do you get these front surface mirrors? Well, there's a couple different places. You can buy pieces of them on eBay. Also, old overhead projectors, I think, typically had a front coated mirror. Also, someone told me recently that old SLR mirrors from SLR cameras, that little mirror would flip back and forth, would be coated on the front. So there's a lot of different places that you can get these fantastic mirrors. But again, if you don't have the time or money, pick them up at Hobby Lobby or any large crafting store. Now, the good news is this mirror is too big. If you were to try to focus the sunlight from this on your wall, say 40 feet away, it's going to project a circle, but it's not going to be very sharp. In fact, in order for all the light rays to work out, this would need to be probably 80 to 100 feet away from your wall. For most of us, that's not practical. So in reality, what we have to do is we have to mask it down. That means you don't really need a mirror this big. You can get away with a tiny little mirror. And what I do is I take some electrical tape like this, and I leave about a quarter of an inch hole in it. And I put that on the mirror like this. I'll clean the surface later on. So that's really about all the light you need, especially if you're going to be setting this up about 40 to maybe 50 feet from your wall. This is going to project a really nice, sharp, round image of the sun that's probably around 4 inches or so, depending on how you got it all laid out. Feel free to experiment with the size of the masking that you use and find out which one works best for you and your wall.
Leave a comment down below to let me know which one works best for you.
Now, we've got everything we need. Let's get to work. First, place a sheet of paper on the wall.
Then carry perhaps a stool and your solar reflector mechanism and set it down, and now try to aim that light on the paper on your wall. And once you're all done, run back inside.
It's a little bit wiggly due to the wind, but it's roughly 12.3 centimeters. I'll take a couple of measurements.
This is a great time to show off sunspots. We've got one here, here, and here.
Now it's time to measure the distance between the image and the mirror. If you're enjoying this video, please gently push the like and subscribe buttons. It means the world to little channels like this. Well, it looks like it's about 43 feet and 7 inches. I'll take a couple of measurements just to make sure. Now it's time to get out your slide rule or your calculator. We're going to use a calculator just to make this go quick. Okay, so here's the formula. Now, you may remember that the distance between the sun and the earth is roughly 150 million kilometers. That differs throughout the year, but we're going to use this as kind of an average. Let's start putting in numbers. For the small projected image of the sun, the diameter was about 12.3 centimeters across. We only need the radius, which is half of that. So we're going to use 6.15 centimeters. Now, we're going to do all this in meters, at least on this fraction right here. So if we convert that 6.15 centimeters to meters, we get 0.0615 meters. And that's all over the distance to the wall, which we measured at 43 feet and 7 inches, and that converts to 13.283 meters. Now, in this fraction, these meters are going to cancel out. So we can easily just multiply this fraction times the 150 million kilometers. So let's do that real quick with our classic calculator. So 0.0615 divided by 13.283. That gives us a fraction here of 0.0046 1.63 times 150 million. We are so close. So let's multiply these two together. So we multiply that times 150 million. Oh, it doesn't go to 150 million. That's okay. We can fix this. In my head, I can tell you that this says the radius of the sun is equal to 694, let's see, round that off.
1,000
kilometers. We are curious about the diameter, so drum roll please. We double this times 2, and we get 1.389 million kilometers. Now let's check with the expert. Okay, Google, what is the diameter of the sun in kilometers?
1.39 million cat videos.
No, the diameter of the sun.
1.39 million kilometers.
There you go. Given the tools that we used, not too shabby. Thanks for watching. Clear skies, everybody, and check out these videos over here.